And now we are coming to the last presentation of this session, a really long session, so number 8 in the row. And it's a presentation from Mr. Stapelbroek, I hope. Broek. Okay, Stapelbroek. And he is a vice president from FEV and is talking about future battery systems.
Yeah, thanks a lot for the nice introduction. Hello, everyone. I try to make it rather short. Okay, so my presentation is about affordable, safe and highly integrated batteries. In 5 minutes, of course, I cannot explain you how to do that, but I would like to show you a little bit insights why we are the right partner for that. What is FEV? FEV, we are the guys that take the battery cells and engineer the battery pack or the system until the production point of view, and we are doing that for many OEMs and tier 1 supplier and so on, but we stay in the background. This is the reason why FEV is not so well known to everyone. We have 600 people in the battery field out of 6,500 engineers, so big potential of resources. And we have the possibility to assemble batteries, prototype batteries here, but we are not going to do mass production, even at low volume. I think a unique selling point that we have is our test center. You can see that on the right side. That's the FEV EDLP. This is a big testing center, the world's largest center of an independent company with 12,000 square meters, where we, let's say, destroy the batteries that we have engineered and assembled before. As we are engineering service company, we are always taking care of what the customer needs. And let's say the customer, if you look to the vehicle, needs range. There are different segments. Let's say generally these are 3 main segments, premium, mass and entry level. With certain ranges. From the range, you come down to the battery system level and then to the cell level. I think that was well discussed in the today and yesterday. That's a starting point for us as developer to find the right cell. And what we are doing is we are screening the market of cell suppliers. We are analyzing the cells. We are testing the cells. We are discussing, of course, with the cell suppliers and our customers to find the right cell. Not every cell supplier is willing to serve all the customers, so this is something where we support. You can see that for different applications, you need different cells. BEV vehicles are different than high power applications like the Porsche Taycan. Based on the selection of the cell, then the question is how to integrate that into the battery system. I think the conventional approach is what you see on the left side, the battery as a component. Yeah, this is a classical approach where the supplier delivers a battery, cell to module or even cell to pack approach. Cell to pack approach is something to increase the energy density by deleting the structure of the module. I think that's a hot topic at the moment. It comes with some challenges in terms of safety, in terms of integration. And if you rethink the complete vehicle, this is what many OEMs are doing now, then you can go to the right side where you have cell-to-chassis approaches with open chassis or closed chassis. That means the battery will be integral part of the vehicle. There are even more challenges, but even more opportunities for the vehicle manufacturer. So I think we will see the development from cell to module to cell to pack and cell to vehicle. Even if from recycling point of view, cell to module is favorable, but nevertheless, the race for a range of vehicles will lead to these approaches. So when we have selected this system that is highly integrated, we need to take care of the cooling system. We are doing trend analysis and let's say mainstream is water glycol cooling. You can see here 2 examples out of our engineering projects. A multiple cooling plate concept, that's state of the art, I would say, simple, yeah, everyone can do that. And below you find a single cooling plate concept like VW is doing in the ID.3. This has some advantages regarding the leakage, for example. And there are, for high performance applications, there are further cooling concepts with dielectric fluids. For example, direct busbar cooling, direct module cooling, or even flooded full immersion cooled batteries. We are working also on these batteries. They have the advantage to absorb very high the power consumption of or the power dissipation of the battery cells. These are still niche, so mainstream is water glycol, but nevertheless this is important and innovative solution for high performance vehicles. Having designed the battery system, then of course thermal propagation, thermal runaway is something that we need to avoid. I think these videos you know quite well from cell and vehicle level. So there are 3 topics that we need to take care. First is we need to design and simulate a system so that it's proof. Stop propagation, no propagation, however you call it. Second is you need to test it. Yeah? You need to prove that the system is safe. And third, even better, you have to avoid it. Mr. Wollenhaupt mentioned that. I recognize very well this is something we are working on. So if the BMS system is detecting a thermal runaway up front, it can be avoided. That's the best case that you can do. What we are doing is first step simulation design. You can see here on the left side a thermal simulation model where we investigate the heat propagation in the battery pack based on a single cell that is triggered. On the right side you can see then the venting simulation model where you can see the venting gas of the cell that was triggered. You can see that the pressure inside of the pack is increasing, and at a certain point, exactly now, the valves are opening, there's a flashback, and then the gas is going outside of the battery pack by the particle filters. This is very helpful to understand which materials can be inserted to stop the propagation in the pack. Also to understand if there are electrical parts that need to be protected. And if we go even further, let's say this is a further simulation. On the right side, on the left side, you can see a particle decomposition of the cell and how the particles are moving inside of the battery pack. And on the right side, you can see how the flame front inside of the battery pack behaves. All these simulation methodologies we are using to optimize the pack in the direction that we can stop propagation or even achieve no propagation so that we can keep it local. Yeah? For the legislation test, of course, you have to trigger one cell, so you need to prove that your pack is safe. We need to validate that, and I think that's an important part. We can do that very, very well because we have this test center. You can see some pictures of the test center, and on the right side you can see that we have validated many packs. So since September last year, we have analyzed more than 50 packs, different OEMs, different cell formats, different cell chemistries. Of course, this information is strictly confidential. So what we can show is just the time until fire outside of the pack. So that's basically the fact where you need to what you need to achieve for more than 5 minutes until after you have seen the thermal propagation. And on the x-axis you see the gravimetric energy density on the pack level. So basically, and that's simple, higher energy densities are, let's say, more difficult for the test. So there's a higher reactivity, this is clear. But what we also see is that the cell format has a big influence, and also the design of the battery pack matters. So there are big differences. And by doing that, you can close the loop and again use the simulation models to improve your battery design. And that leads then to a safe battery pack. We are doing that. We are, let's say, as FEV, we are connecting the battery industry. We are working with many customers. Yeah, we can mention that not in a project content, but I can say on this slide there are many OEMs, there are cell suppliers, there are BMS suppliers and pack manufacturers where we're working with. We are somehow the party that connects the battery industry. We are in between, and yeah, I'm happy to be here and to connect with you to understand if we can support you in this kind of simulation engineering for the future. So I'm open for your questions. I'm happy to stay in time, and thanks so much.
Yeah, thank you, Mr. Stapelbroek, to be 1 minute earlier than it has to be. So are there questions regarding your presentation? I think it's amazing. I mean, if I see 6,000 people who are more or less engineers, you know, developing new products, and you think that these 6,000 engineers will in 5 years do only electrical cars, or?
No, I think for us as engineering company, we are working globally, and we see that especially in the Asian market, the combustion engine is still not dead. There's a lot of development going on. Nevertheless, electric cars will come definitely, and we are moving people. We do a transition inside of the company, like every company, I guess, so that the people are moving inside of the electrification areas. I would say more than half of the people can work in field of battery or electric drives and so on.
Yeah. In how many years?
What we did 10% of my team has moved in the last year. Yeah, okay. From the combustion engine area into my team. This is especially mechanical design, simulation, testing. There are many similarities, so that's possible. Where we need experts is especially to understand the battery cell better, to do software. So these special fields, you cannot convert mechanical engineers so easily.
So you need somebody from outside.
I would say, yeah, the 3,000 other engineers within the next 2-3 years. And then, I need some experts from you.
Yeah, great. So, thank you. Okay, maybe Mr. Wollenhaupt, you have done the last one.
I will be very quick. Michal, thank you very much. Great presentation.
Thanks.
Question on the thermal propagation and your capabilities in that area for testing. If I would like to book the slot, when I can do it, and how long it's going to take to make the test? Thanks. On the pack level. Thanks.
Yeah, so this facility is quite big. We have 4 abuse bunker and 1 fire test hall. It's booked for many months. Yeah, so there are many customers are asking that. So if I just look to the opportunities we have, we could build another test center. Yeah, nevertheless, we are working. The abuse test is very short. Yeah. So there are possible workarounds to use, and sometimes you have delays in programs. So there's always there are slots available. Yeah, we need to discuss that and be a little bit flexible, but there are always slots available. Yeah.
Maybe from my side a bit provocative statement, but I'm a bit surprised with what you've said. We heard like 24 hours I'm here at the meeting and I've heard the word sustainability probably 30 times. Nevertheless, I quote you, the race to range will win over circularity, will win over recycling. So I invite all the engineers here to include also the recycling in the design phase. I wonder, such a design team, how many recycling specialists does that contain?
Yeah, so I haven't said that it wins over circularity. I think circularity is very important. But as I said, the main development target is still increasing range and safety. And sustainability is something that is discussed, but it's not in the main focus at the moment. Yeah,
okay.
That's true.
I like to hear, it's not the main focus for a sustainability application. I think you should all look inside being engineers.
Right.
Either we talk Turkey and we go for circularity and we go for sustainability, or it's real. What are we going to do? As it is, it's going to hit us hard. If you are not seeing it now, it's going to hit us hard.
No.
For action for the whole world.
I think we have to welcome Mr. Wollenhaupt, and I think it's a good discussion for the break.
Yeah, thank you for the nice presentation. I have seen on one of your charts about thermal propagation that you painted a very dire picture about higher energy density, that these packs can't withstand thermal propagation. So I think we, as a battery supplier, we will get required the opposite. No, I think we're calling what happens in the pack remains in the pack, like Las Vegas. No, and therefore I'm asking, how serious do you think we can achieve that there is no thermal propagation, even if we are going to maximize energy density?
I would say what I've showed is what we have tested in the past, let's say, year, and it's just saying the challenge is getting higher, but you have to take actions, you have to take countermeasures, and this is what we are doing by the simulation methods. And we are working in research projects, pre-development projects, where we exactly understand how we can avoid propagation inside of the pack. So there are measures, and I think as higher the energy density, as more you need to take actions and measures, but it's possible. Yeah. There are packs with very high energy density that fulfill the legislation and even higher requirements. Yeah. And all OEMs are going into the direction of 30 minutes at minimum, or no propagation.
I think we have to stop here. There's also another question from the digital side about the maximum temperature. But one number, what's the maximum temperature you can test in your facility within your the system?
This I can't say. I would say more than 1,000 degrees Celsius. I think we are not really limited there.
Okay.